Confused about experimental uncertainties in physics? Confused about all the different terminology? In this video, I will demystify experimental uncertainties for you. I will discuss how we quantify them, how we use them, and how we talk about them. Throughout the video, I'm going to use an example where a group of students, Group A, are conducting an experiment to determine the speed of a battery-powered toy car that moves at a constant speed across the floor of their classroom. Let's imagine Group A determine the speed of their toy car by measuring out a 1 meter length on the floor with a meter stick that measures in millimeters. They run multiple trials using a stopwatch that measures in hundredths of a second, timing how long it takes for the car to travel this 1 meter length. After 5 trials, they get the following results. Let's look at these time measurements. How can we communicate these data concisely and meaningfully to others? First, you might suggest we can take an average of the measurements. But you also notice there is variability in the data. None of the measurements are exactly 3.12 seconds. The highest time is 3.40 seconds and the lowest is 2.84 seconds. How can we describe this variability? We need a way to quantify the spread of these data about the average value. There are various ways to do this with varying levels of correctness, but a simple and easy way is to take the largest value in the data set minus the smallest value and divide by 2. Putting these numbers into the equations gives a spread of 0.28 seconds. Group A can now write their time measurement as 3.12 seconds plus or minus 0.28 seconds. Notice I dropped the last decimal in the average. That is because the uncertainty is 28 hundredths of a second. Keeping the 4 conveys a level of precision, thousandths of a second, that you simply don't have. More on this as we continue. It is important to pause and understand what is being communicated when Group A writes a measurement of 3.12 seconds plus or minus 0.28 second uncertainty. It communicates a confidence interval for the measurement. 3.12 plus or minus 0.28 communicates that Group A are confident that the true time measurement lies somewhere between 2.84 and 3.40, with their average lying at the center of this confidence interval. Whenever you take multiple measurements and see some random variation above and below some average value, we say that the uncertainty is random uncertainty. This refers to the source of the uncertainty, which is arising from random variation in the experimental conditions. Now, how about the uncertainty in the distance measurement? Group A measured the distance of 1 meter. You notice that Group A only measured their 1 meter interval once. What if they went back and measured the distance several more times? It is likely they will measure the same 1 meter distance every time. If Group A takes repeated measurements of the distance and gets the same number every time, does this mean that there is no uncertainty in the measured distance? No. What it means is that the random variation in the distance measurement is smaller than the ability of the instrument to measure it. The measuring instrument in this case is a meter stick, and if you look at the meter stick, the smallest tick mark is a millimeter, which is 1/1000th of a meter. This is a different source of uncertainty, which we call instrumental uncertainty. If repeated measurements of a quantity give the same reading every time, we say that the uncertainty is less than half of the smallest unit that the instrument can measure. In this case, the uncertainty in the distance measurement is less than half of 1/1000th of a meter. Generally, we don't use a less than sign and replace it with an equal sign. Just remember that 0.0005 represents an upper bound on the uncertainty in the distance measurement, but it is reasonable to say that we are confident the true distance lies between 0.9995 meters and 1.0005 meters. This is also why I wrote the distance measurement as 1.000 meters. Keeping those 3 decimal places conveys to others that our instrument, the meter stick, is measuring to thousandths of a meter or millimeters. One question or confusion that often arises is this. The stopwatch measures to hundredths of a second, so why don't we write each time measurement with an instrumental uncertainty of plus or minus 0.005 seconds? The answer is that the random variance in our experiment is far larger than the instrumental uncertainty. Consequently, the instrumental uncertainty of the stopwatch is irrelevant to estimating the uncertainty in the time measurement, and it makes no sense to quote it in the measurement table. Group A now uses this distance measurement and time measurement to calculate the speed of the car by dividing the distance traveled by the time taken, resulting in a calculated speed of 0.320 meters per second. This brings us to the most important question of this video. If I have two measured quantities and these two quantities have known uncertainties, and then I use those measured quantities to determine another physical quantity, the speed of the car, what is the uncertainty in the calculated speed, given the known distance uncertainty and the known time uncertainty? Answering this question could take an entire textbook, but I'm going to discuss a simple rule of thumb called the weakest link rule, taught to me by Alan van Huvelen. The weakest link rule says that whichever measured quantity is the most uncertain, the calculated quantity, which is the velocity in this case, is as uncertain as the most uncertain measured quantity. Let me unpack that statement. So far, we have talked about how uncertain something is as a plus or minus value. We have discussed that this defines a confidence interval for each measurement. 3.12 plus or minus 0.28 communicates I'm confident that the true time measurement lies between 2.84 and 3.40 seconds. But the question we need to address now is, how uncertain is the time measurement, and similarly, how uncertain is the distance measurement? To answer this question, we need to take a little detour. Imagine you're given a meter wheel that you can roll along the ground and it clicks once every revolution so that each click represents 1 meter of distance traveled. Thus, the instrumental uncertainty of the meter wheel is plus or minus half a meter. First, you measure the width of your bedroom with the meter wheel. As the wheel turns, you hear 5 clicks, so you estimate that your room is 5 meters plus or minus half a meter wide. Now imagine you are asked to measure the circumference of Earth around the equator with the meter wheel. Let's imagine you can do this, ignoring all the mountains and oceans and other obstacles that might get in your way. After a very long walk, you measure the circumference of Earth is 40,075,126 meters plus or minus half a meter. Let's pause and ask, which of these measurements is more precise? While both measurements have an uncertainty of half a meter, measuring the width of your bedroom to the nearest half meter doesn't sound very precise, but measuring more than 40 million meters down to the nearest half meter feels extremely precise. How do we quantify these different levels of precision? The answer is that we take the ratio of the uncertainty to the size of the measured quantity. We call this ratio the relative uncertainty. The relative uncertainty in the bedroom width measurement is the ratio of the meter wheel uncertainty to the measured width of the bedroom. You can think of this as a noise-to-signal ratio that tells you how large your variability is in relation to the quantity that you just measured. In this case, the relative uncertainty is 0.1 or 10%. A similar calculation for the circumference measurement shows that the relative uncertainty of this measurement is 0.000001%. You can think of the relative uncertainty as a way to quantify how precisely you measured a physical quantity. It communicates to other scientists how good of an experiment you conducted in terms of the precision of your measurement. In this experiment, the circumference measurement is much more precise than the bedroom width measurement. Let's return to our previous example with the toy car. To implement the weakest link rule, we need to identify which measurement is more uncertain, the distance or the time measurement. So, let's find the relative uncertainty in the distance measurement and the relative uncertainty in the time measurement. Plugging in numbers, we see that the distance measurement is 0.05% uncertain and the time measurement is 9% uncertain. The weakest link rule says ignore the 0.05% and keep the 9%. If the time is 9% uncertain and this is the dominant uncertainty, then the relative uncertainty in the calculated speed must be 9% as well. In the final step, we want to find delta v, the actual plus or minus uncertainty of the speed. To do this, we multiply the calculated speed by 0.09. The uncertainty in the speed is 9% of the calculated speed, which is 0.03 meters per second. Group A can now report the results of their experiment to the rest of the class. They should write in their lab report that they determined the speed of the toy car to be 0.32 meters per second plus or minus 0.03 meters per second. Finally, let's discuss why we need uncertainties and what they are useful for in physics. Let's suppose the students measure the speed of their toy car to be 0.32 meters per second plus or minus 0.03 meters per second. As discussed before, Group A are communicating a confidence interval. They are confident the true value of the car's speed lies somewhere between 0.29 meters per second and 0.35 meters per second. Knowing the confidence interval, the measurement is useful for two things. First, suppose I have a theoretical model of toy cars that allows me to predict the speed of the car given certain known input parameters, and suppose that this predicted speed, Vp, is 0.34 meters per second. Now, you might say that 0.32 meters per second and 0.34 meters per second are different numbers, and so you might incorrectly conclude that the measurement and the prediction do not agree. This is where the confidence interval comes in. On the number line, 0.34 lies inside the confidence interval of the student's measurements. Therefore, there is a high probability that the actual measured speed of the car is 0.34 meters per second. In this case, we conclude the student's measurements agree with the predicted value. As long as the predicted value lies anywhere inside their confidence interval, the students should conclude that the experiment and prediction agree with each other. On the other hand, if the student's measured speed was 0.40 with a plus or minus of 0.03, you can see that the predicted value lies outside of their confidence interval, and the students should conclude that their measurements disagree with the predicted speed. Another possibility is that we need to compare measurements made by different groups of students using different measuring methods. Suppose Group A measures the velocity to be 0.40 plus or minus 0.03, and Group B, conducting a different experiment with a different method, measures the velocity to be 0.30 plus or minus 0.05 meters per second. We can draw the two confidence intervals on a number line and look to see if they overlap or not. Here the two confidence intervals do not overlap, so the two groups should conclude that their measurements disagree with each other. At this point, even though the two measurements are quite different from each other, the confidence intervals of the measurements overlap, and therefore the two groups should conclude that their measurements agree with each other. At any point where the two confidence intervals overlap, the measurements agree with each other, and when they don't overlap, the students should conclude the measurements do not agree with each other. And this is why we need uncertainties. When we measure stuff, it is never exact. We need to know when measurements and predictions agree or not, or when two sets of independent measurements agree or disagree with each other, bearing in mind that two numbers will almost never be identical. Hopefully you found this video helpful and that you better understand the purpose of uncertainties, how to estimate them, and how to propagate them using the weakest link rule.